massive machine, but it's a real piece of precision engineering too.
From the moment we launched the kit to make the first internal module, right through to the engine being dispatched, it's 20 days.
The fan blade delivers 75% of the engine's thrust. It shifts about 1.2 tons of air per second when it's at full throttle.
After about 30 seconds, you've got to come away. You can't stand there too long. If you do, you just start burning.
Every bit of this is all put together by hand.
We used to fit a bolt that was wrong. The aircraft was to come down.
We run thousands of hours of testing. An explosive detonation releases the blade from the disc at max takeoff speed and fires it into the fan case. The engine is destroyed.
Derby is Rolls-Royce. You mentioned Derby, everybody says Rolls-Royce.
They do very well with the line, very fast with the line. They don't need more Rolls.
Morning. That's the inspection department, very friendly people there.
It's a very tough competition with one of the most powerful and competitive companies in the world in General Electric.
It's not until you see Trent Fleet fly over. I've made my own bit of that.
Today, we're the lead. We're the most efficient engine flying in the world.
This is the Boeing 787 Dreamliner.
Cap 35, cross runway 11, 200 to the ramp.
Designed to be the most fuel-efficient jumbo jet ever, it's touted as the future of air travel.
Even in sort of a grey Seattle day, that paint job is beautiful.
After years in development, the plane is finally ready for its very first flight. The weather's atrocious, but it's a make-or-break moment for Boeing's first new airliner in 10 years.
You know, our plane is taxiing, and so we're proceeding inbound. I'm switching to...
And no one's more gripped than these engineers watching live over the web in Derby. Because they have designed and built the plane's groundbreaking jet engines, using technology that'll save each plane £3 million a year in fuel. If the flight goes according to plan, Rolls-Royce could find themselves building the greenest, cleanest engine for many of the world's airlines, and securing orders in a highly competitive industry. The engine includes some of the most advanced aviation technology the world has ever seen. This is the story of how a British company leads the world in building the most advanced jumbo jet engines, and of the people who build them. Rolls-Royce jet engines are built at state-of-the-art factories all over the UK. It's a huge operation, with orders worth over £40 billion in civil aviation alone, and employing around 11,000 people building them. A new engine must roll off the production line every 36 hours.
Morning, Kev.
Morning, you all.
All right, mate.
This week it's my turn, but I tend to be more times in a suit than not.
Wow, actually I could be building one of these in maybe a few months, or designing one of them. Maybe one day.
There you go. That's it. Look at that beauty. It's a work of art.
Rolls-Royce's main assembly plant is a vast 300-acre complex of factory buildings in the southwest corner of Derby. The city has been home to Rolls-Royce for 100 years. And for many of the 250,000 people who live here, the company is a way of life, in work and play.
They ensured me that they would arrive today. About 12 years ago, I joined the Rolls-Royce Ladies Choir. Start spreading the news. We rehearse every week on a Monday evening at the Rolls-Royce Leisure Association. It's a real enjoyable evening after a day at work.
For many of those who work at the company, Rolls-Royce and Derby go back a very long way.
I was born and bred in Derby, so I've been in Derby 53 years.
I've been at Royce's 36 years. It's like a family business as well, because my wife works at Rolls-Royce.
Without Rolls-Royce, I'm unemployed, you know, so it means a lot to us. Well, I think it means a lot to Derby, full stop, really.
You look up to Rolls-Royce, I bet there's not anybody really that doesn't know somebody that works at Rolls-Royce.
40 years. Since I was 18, I joined Royce's. I actually worked on Spitfire, the Merlin engine.
The choir's been in existence for 50 years. We celebrated the 50 years last year and had a big concert to celebrate that.
50 years and nearly 6 months. They sang at my wedding, and which was very nice, and I came back with my daughter when she was 11 days old, and she sat in a pram and rocked all the while we were singing for months.
Derby is Rolls-Royce. We've got lots of other engineering companies, but you mentioned Derby, everybody says Rolls-Royce.
The company used to be most famous for its luxury cars, but that all ended in the early 70s. Today, Rolls-Royce cars are actually made by BMW. The company's real heritage is aircraft engines. In fact, they've powered some of the world's most iconic aircraft, from Second World War fighter planes and the Harrier jump jet to the much-loved Concorde. And that heritage continues today, powering helicopters, business and military jets, and even ships. But the star product is the pioneering family of Trent jet engines, including the newest Trent 1000 for the Boeing Dreamliner. All the Trent engines are designed for jumbo-style wide-bodied airliners, like Boeing's 777 and the famous Airbus Super Jumbo. But this engine, for the Airbus 330, is the biggest seller of all. In 15 years, the Trent 700 has clocked up 13 million flying hours.
It's a massive machine, but it's a real piece of precision engineering too.
Weighing at least 5 tons, each Trent engine is worth several times its weight in silver. Only 2 companies in the world are capable of building engines this good.
It's a very tough competition between one of the most powerful and competitive companies in the world in General Electric. If you look at all the latest new technology aircraft, all have selected Rolls-Royce engines to power the first flight.
It carries a payload of 242 tons at 37,000 feet for 9,500 miles, which, as you can imagine, is a serious challenge for any technology to deliver. So it really is at the high end of manufacturing and assembly. And I often describe what we do as producing things of beauty.
But the popularity of the Trent 700 is also the factory's biggest challenge. With orders placed to build 400 new engines, the company has to produce at least 4 a week. For their production line, one of the most complex in the world, time is big money. Each Trent engine is built from modules, 8 separate sections which are put together on the assembly line. But each module is made from thousands and thousands of components. And the monumental task of gathering them starts here at their massive parts warehouse.
On average, with my pedometer, I average about 8 miles a day.
on an average day, but if we have lots and lots of issues, my best is just under 16 miles in a day. Lots and lots of shoe leather use.
Kevin Carr's job is to make sure every engine part is delivered to the assembly line on time.
I do know the guys around here say, you know, you just give me a part number, show me a box, and I can tell you what it is and where it goes. Everything's footprinted, ready for the guys. It's a bit like a sweet shop for them. They can pick and choose what they want. We supply the very first nut, bolt or washer that they fit, right up to the very last little bit of plastic that we put on the engine before it goes out the door to the customer. So that could be anything up to 30,000, 40,000 parts, depending on which engine it is.
It's Kev who kicks off every new engine build. 2 days before the assembly begins, he triggers the dispatch of tens of thousands of parts from the warehouse.
So now it's 8 o'clock.
Have we got all the bits there for it?
Yes.
Got all the paperwork?
Yes.
Yeah, so we're all ready to go then. OK, thanks very much, Noel. Looking at the boxes, you wouldn't know, but just looking at the odds and sods that are lying on the floor, there's nothing under £1,000. You've got the engine control management unit, roughly £750,000 worth in that box, just sitting there on a pallet. Anything up to £200 million worth of stock on the shelf. We have roughly 5 engines worth of stock of anything.
Some of the components that make this engine what it is were designed and built by some of Britain's most skilled and innovative engineers at Rolls-Royce. Nestling in the Lancashire Hills, 100 miles north of Derby, Barn Oldswick is where the first ever jet engines were developed by Sir Frank Whittle. And today this small community still plays a very special part in the building of every Trent engine. Raw materials arrive at the factory every day. Solid sheets of high-grade titanium. They're destined to become one of the components that make Rolls-Royce Trent engines truly unique.
When you walk onto a plane, you look into the engine, that's the fan blade, and that's what we make here.
Mike Wallace's job is to transform the raw metal into high-performance fan blades.
The fan blade delivers 75% of the engine's thrust. It shifts about 1.2 tons of air per second, and the loading on the blade is something like 90 tons centrifugal load when it's at full throttle.
That's like hanging 13 double-decker buses off each of the 20 blades. The enormous fan is what distinguishes a modern jumbo engine from older turbojets. They didn't have a fan at the front and relied entirely on the jet exhaust to thrust the plane forwards. Faster than a propeller, but inefficient and very noisy. But in a turbofan, like a Trent engine, the energy of the exhaust is harvested to turn the massive fan blades at the front, which in turn push huge amounts of cold air quietly around the sides of the engine. And that's what thrusts the plane forwards. The Trent fan blades are unique.
So, which section is this?
And it's all down to their design.
The original blades used to be solid, but in order to get better performance, take weight out of the engine, it was designed to be hollow, and our manufacturing process, which is unique, has actually enabled us to make that and advance the technology within Rolls-Royce.
Every single fan blade is worth as much as an average family car. For each blade, 3 sheets of metal are bonded together to make a solid titanium sandwich. It's a process so secret it can't be shown on television. The unique process begins when the titanium layers are bonded together in a secret pattern. Then the whole blade is inflated like a balloon, pulling and stretching the inner layer across the cavity, like cheese between slices of pizza, leaving a super light, super strong internal structure. But before it can be inflated, the flat titanium sandwich has to be heated and twisted into shape. Then it's ready for the most critical stage of the process, inflation.
We've used an inert gas. We can't have it reacting with the titanium at temperature. It's a high pressure inside to inflate it to the level of accuracy we need.
A heat-resistant tube connects the blade to a high-pressure gas supply. But the gas alone won't be enough to inflate the blade. The whole assembly also has to be loaded into a furnace at a secret, critical temperature. A single speck of dust could cause a lot of damage. And John doesn't get much time to prepare.
It gets very hot. After about 30 seconds you've got to come away. You can't stand there too long at all. If you do, you just start burning, you know, your gloves, fingers, everything.
It takes 4.5 hours for the gas to slowly inflate the blade to its precise aerofoil shape. Despite the precision of the engineering, no two finished blades are exactly alike. And with 20 in each fan, it will only spin smoothly if the blades are perfectly balanced. So every one is precisely measured and weighed, then rung like a bell.
Each blade has a different mass and different frequency, and we use that data to select where those blades are going to be positioned within the disc. So when we go to engine build, they're located and selected in those exact locations.
This is the attention to detail that ensures every Trent engine is as safe and efficient as it can be. And with up to 150 blades leaving the factory every week, it's also the challenge that keeps Mike going.
For me, it's exciting. After 27 years working on fan blade, it's still exciting. There's still a lot more to do.
Rolls-Royce is a global company. Some parts of the engine are made and assembled at factories abroad. Getting them to the UK is Kath Taylor's job.
This is the turbines purchasing department, where we source parts from all over the world, and my role in particular is to source the modules from mainland Europe. We're talking probably at the moment about 10 modules a week. Very occasionally we're affected by the weather or the ferries, but the bulk of the modules do arrive on time.
It may be a global company, but the biggest single module is manufactured at another of Rolls-Royce's specialist factories just 50 miles down the M1. Mark Reed is in charge of building the massive protective case that shields every engine's fan blades.
The fan case's primary function is to guide the air through to the main core of the engine and to provide a containment system in the event of a blade off. When the forging's originally constructed, it weighs 5 metric tons in weight, and then when it's finally finished machined, it weighs roughly 500 kilos. So we have to take a large amount of material off, and we have to machine it down to some very fine tolerances. Typical wall thicknesses can be around 2.5 millimetres. There's a number of different processes that take place, typically around 40. A component can spend up to 90 hours in the machine. So we put it on at the beginning of the week and we take it off at the end.
And nothing goes to waste. Every sliver of precious material is collected and recycled to make more components. Mark runs a team of 140 top engineers, including experts in the most essential skills, turning and welding metal. One of the most experienced is welder Bob Blackwell. His job is to fix in place a ring of titanium blades that'll channel air smoothly into the engine. It's a highly specialised form of welding.
I'm a TIG welder, come sheet metal worker. I've been doing this job for 22 years now. All these vanes are different cambers to achieve the best airflow. Every weld on this job will be x-rayed in the x-ray, so any defects have to be taken out, obviously repaired then and put right. When this weld's finished, this vane should leave a tolerance of no more 5 mil radially and 1 mil forward and rearward on the blade. It's not machine, it's hand skill, and we think that's a fine tolerance to achieve on a hand weld.
Bob works at the factory alongside his son, Lee.
Lee's a sheet metal worker, they're just the same as myself. So when Rolls were recruiting, I asked me if he fancied joining the company.
I see my dad made a good living out of it, so I decided to get a trade and just get the same trade, really.
Lee's a better welder than I am, better craftsman than I am. He don't need that. He don't need my voice, he's quite capable on his own, really.
For this family partnership, the factory life certainly seems to promise a good future.
Yeah, I hope so, yeah. I wouldn't like it to come to an end too soon,
At the heart of every engine is a ring of 96 turbine blades that are the most amazing components in the whole engine. Jet engines work by sucking air into the core and through multiple compressors. Squashed to a 50th of its volume, this air is forced into a combustion chamber, where it explodes with fuel to create a ferocious gas jet. This jet is met head-on by the turbine blades, spinning them so fast that each blade delivers the same horsepower as a Formula One engine. The job these tiny blades have to do is unbelievably demanding.
The blade exists in a fairly harsh environment. It has to rotate at about 10,000 revolutions per minute, with a blade speed of about 800 miles per hour. The component itself operates at something like 300 degrees above the melting point of the alloy.
To operate at around 1700 degrees, they're designed not to melt.
Here you see the gas streams moving around the airfoil. At the bottom of the blade is the fir tree area, which is used to hold the blade into the disc. Above it you see the aerofoils with a peppering of cooling holes.
To stop the blade melting, Rolls-Royce designers used computer modelling to design a blade that has a precise pattern of tiny air passages throughout.
Here we see what the blade would look like if we didn't have it cooled. And you can see that there are some areas of red, which means that the component is too hot. We put a cooling system inside of the blade, which cools it down to safe levels, and that cooling system takes away the same amount of energy that would boil a kettle in a 20th of a second.
But even with the cooling holes, no ordinary metal would be good enough. That's where the company's Materials Research Laboratory comes in, creating new metals with exactly the physical and chemical qualities demanded by the designers.
To try and achieve the properties that the designers want, we will design some trial compositions of alloys with different recipes, different blends of the alloy constituents, and then we will test those samples and different mechanical and environmental tests, and from that we'll choose the best possible blends which will deliver exactly the balance of properties that they require.
Using electron microscopes, the materials scientists can precisely analyse the microstructure of the alloy, checking that the crystal structure and mixture of metals is exactly as intended.
We've got a team of research specialists, about 25 in the team here in the UK, and there are teams in Germany and the States as well. And we're trying to draw on all the expertise that exists in the academic network around the world to bring all the best expertise we can into Rolls-Royce.
Even the finely balanced alloy recipe isn't the most advanced technology in the turbine blade. To cast the metal into its complex shape, a unique process is used, and it's another very closely guarded secret. It's done at a purpose-built foundry in Derby, where one of the few people who knows the secret is casting engineer Owen Draper.
If you take a normal piece of metal and solidify it from being molten, you'd end up with something that looks a bit like a granite worktop. Lots and lots of little different crystals, all in different directions. That's not very strong because the different crystals, the joins and the boundaries between them, they just cause a weakness. So what we aim to do here is to create a single crystal. Single crystal, no crystal boundaries, therefore it's an awful lot stronger.
The blade is made by growing a single crystal of metal into the correct shape. It's incredibly complex and demands a huge team of people working round the clock. But it starts with an intricate, hand-built model of the blade in skilled hands like Maureen Hankey's.
I've been doing it on and off since '73. Skill is you've got to be very dexterous, everything's got to be perfect, everything's got to be smooth.
The secret part is the way the molten metal is cooled through a spiral tube at the base of the mould. The tube prevents all but one crystal of solid metal from passing through, allowing that single crystal to grow throughout the mould. Imperfections could ruin the casting at any stage. Even the wax models are X-rayed by keen-eyed inspectors like Jackie Brown.
We're looking for defects in the core, i.e. cracks, chips, voids. When it's sentenced to scrap is broken in half and put into the bin.
Once cast, every single blade is thoroughly checked, and checked again. By eye, by computer, and by X-ray. Even then, they're far from ready. Each blade goes through another 4 days of precision finishing in the hands of machinists like Steve Ball.
We're all very good at what we make. We don't sometimes share it. It's not until you see Trent Fleet fly over. I've made my own good bit of that.
And because of the extraordinary demands on the blade, its dimensions must be accurate to within 1/10 of a hair's width.
We grind the fir tree to within 7 microns, which is a hell of a tight limit. Goes under a load of 18 tons, that does. If we stretched it with 18 tons, re-gauged it, there would be nothing. Everything would be to the micron the same. There's no alterations in the structure. There's no cracking. There's no stretching of anything on there. And bearing in mind, you've got 96 of those in an engine set. Every one is like the first one. It's perfect. It's like a brand new baby. You treat it like that. That's why the focus of everybody in the shop's the same, whether it's 6 in the morning, 6 at night, 12 at night. Everybody's the same. The next one's always the most important because all the rest are good. Because we've never had one come back. You can't argue with that.
It's the skills of people like Steve and the cutting-edge technology that keeps Trent engines ahead of the game. But innovation is a risky business. Designing the Trent engine almost brought Rolls-Royce to its knees. In the early 70s, the company risked everything on a revolutionary new engine for one of the world's first jumbo jets, the Lockheed TriStar.
The production programs at Derby, by modern-day standards, were very low in volume, and Derby was, a relatively small player in the aero engine market, although the only player outside of the United States in the commercial market. So getting the TriStar program was absolutely vital.
As a small player, Rolls-Royce had big ambitions.
Well, the 211 was quite an advanced engine concept, even by the standards of the day. It was the first 3-shaft engine, whereas the competitors were offering 2-shaft engines. So as well as the technological advances, it was a completely new architecture.
The design made the engine lighter and more efficient. It promised a crucial reduction in running costs and cheaper airfares. But actually building the engine proved harder than anyone expected, and the costs spiralled with every advance they made.
And all of these were put together in an engine number 10,011, which ran on February the 3rd, 1971, late in the afternoon. And the results were quite exceptional in that they were very much better than anything we'd run before. So understandably, we were quite elated.
It seemed the company was about to achieve its goal with their new engine, but the elation was short-lived.
Until the next day, when in the middle of the morning we were all invited to go into the office and the announcement was made that the company had gone into receivership.
It was too late. The project had bankrupted the company, and Derby was in crisis.
There's hardly a family in the town that hasn't got someone working at Rolls, not just as manual workers and skilled craftsmen, but as research workers and designers. When the men came out at lunchtime, they were obviously shaken.
Shocked. Just shocked.
Looks very bleak, that's all I can say. I mean, looks very bleak, doesn't it?
Did you ever believe this could happen here?
Never. I've been here 27 years and I've never thought anything like this could happen.
I think the government ought to really back us up a little bit. Quite a lot, because it's a household name, isn't it, Royce's?
The government came to the rescue, saving thousands of jobs and giving Rolls-Royce and the people of Derby one last chance.
The progress that was made during the following 12 months, 14 months post the bankruptcy was quite remarkable. And we actually managed to get the engine into service at the end of April 1972.
When the TriStar finally flew, the hard work and revolutionary technology paid off. The engine became the jewel in Rolls-Royce's crown. And it still is today, as the basic design of the entire family of Trent jumbo jet engines. Launching Rolls-Royce onto the international stage, the engine helped them grow from a small player to a global competitor. Today, Trent engines are fitted to half the world's big passenger jets, with new orders worth over £40 billion. At the heart of the Derby factory is the main assembly line for all Trent engines. The line has to run like clockwork to take every build from first components to completed engine bang on schedule.
From the moment we launched the kit to make the first internal module, right through to the engine being dispatched, it's 20 days.
The countdown starts with assembly of the biggest and most complex modules. Hundreds of precision-tooled blades, hand-fitted and finished to perfection. 4 days in, and work begins on the engine's Kevlar-wrapped aluminium fan case. Over 4,000 engine control and transmission parts, fitted and wired, every one by hand. At the same time, an army of expert fitters begin the 9-day task of fitting together the engine's 8 separate modules. The first 5 sections are stacked one on top of the other. With gravity helping the process, it's a lot easier to achieve a perfect fit. Every bolt is adjusted to a precise torque, and there are moments that require absolute concentration.
Going down.
We're having to pass through the whole of the O4 module before we arrive at the coupling in the O3 module, and we take all the care we can not to touch the sides. If it ticks the paint off the shaft, then we have to recoat the paint for protection. It's the trickier of them all to fit, mainly because of the coupling that you can't see and the adjustment that's needed.
Going down.
And there's the two shear keys that will ride up and locate in the slot. You should hear as it clicks. They've clicked in now.
1 week into the build, the fan is assembled from its kit of blades. And with each one worth as much as a family car, it takes an expert touch.
We prefer to wear gloves. It keeps fingerprints off the blades and this grip as well. So it does stop them slipping out of your fingers.
You don't want to drop it, do you?
Certainly not. Certainly not.
Before the fan can be fitted, the towering engine stack is craned onto its side. Two tons of precious metal swinging just feet from the ground. Finally, in the position it'll spend the rest of its life, the engine's ready for the last two and biggest modules. The fan is a perfect fit. Its tips clear the lining of the case by a fraction of a millimetre, yet in flight will spin faster than the speed of sound. After 2 weeks of assembly, every completed engine is fitted with vast aerodynamic ducts and inched across to the factory's purpose-built flight test centre. Here, it'll be fired up and put through its paces in a simulation of the harshest flight conditions.
3, 2, 1.
While engineers monitor vibration, rotation speeds and temperatures to ensure everything performs perfectly.
Vibration is looking good. Max conditions now, hands down to 1. 3, 2, 1, go.
Signing off newly built engines isn't all they do at the test centre. Dave Benbow is in charge of testing prototypes for new engine designs before they ever take to the sky. And that means carrying out tests that are much more challenging.
We run thousands of hours of testing. Our primary requirement is to show that the engine is safe to fly, that it's airworthy. We conduct a number of tests to do that, but really we're trying to meet the regulations of the safety agencies. This engine is a flight test engine, and in that extent it has a lot of instrumentation that production engines wouldn't have, that you can see here is led up off the engine and into the pylon so that we can record the data on the test bed when it's installed.
Testing is so exhaustive, it can take 2 years for each new design.
The cold start test is a very important test. We need to be able to start the engine under cold conditions, cold as minus 40 degrees.
Removed from its giant freezer, everything must still work perfectly when the engine is started.
we have to make sure that the gearbox will turn when we start the engine. Other tests, so water ingestion.
Water is poured in at 30,000 gallons an hour, but there must be no loss of thrust.
We have to demonstrate that the engine can cope with rain and hail ingestion, and that the compressors can cope with the amount of water going through the engine that it might get in flight, and that the compressors continue to run and that the combustion system remains stable. But one of the key safety requirements we have to ensure we meet is that in the unlikely event of the release of a fan blade, that it's contained by the fan case. Well, it's an absolutely key test in that we need to make sure that there's no chance of the fan blade escaping. On the test, there's an explosive detonation which releases the blade from the disc at max takeoff speed and fires it into the fan case. When this event happens, the energy that's generated by the blade coming off is about the equivalent of a 1-ton car being dropped off a 200-foot cliff. And the casing here then has to retain that and ensure that nothing is released outside of the fan case structure. So it's a hugely expensive test, but our commitment to safety and demonstrating requires us to take that asset and to complete that test, irrespective of what we're left with in the end. The engine is destroyed. Although it's contained the blade and run down safely, the components that are in that engine will not be used again. Effectively, that engine is then written off.
Only by sacrificing an entire engine like this can they be sure the fan case really does its job. It's 6 in the morning and the start of another shift on the assembly line for fitter Andy Taylor.
I just wait round the corner from here, so I work on where they build the stacks. Work 3 shifts. Work mornings, afternoons and nights. I'm on mornings this week. Morning. That's the inspection department, very friendly people there. This is my engine for today.
Andy's task today is to fit the first of a network of sensors to the engine.
These are connected to the thermocouples. And these tell the brain of the engine that if there's an overheat problem, it'll tell it to like alter something inside the engine to cool it down, or vice versa if it's running too cold.
When it's running, these sensors will measure temperatures, pressures, speeds and vibration at critical points in the engine. The sensors constantly feed that information to the engine's own electronic management system, its brain, that ensures performance is optimized at all times. But it doesn't stop there. Data collected from every Trent engine in the air can even be transmitted via satellite back to Derby. It's received here at the factory's 24-hour monitoring station, manned by senior engineers to keep an eye on Rolls-Royce engines all over the world.
Alan, we've got an issue on engine 41992. We can just see that the exhaust temperature's just going up on that engine.
This is 21st century jet engine production, part of a high-tech support package that gives them a commercial edge over competitors.
Increasingly now, as the airline buys a Rolls-Royce engine, we secure a service package with them, sometimes for as long as 20 years, where we will provide all the maintenance, all the spare parts for their engine. We will make sure they have engines available whenever they need them to support their aircraft, and they simply pay for the number of hours they fly.
At peak times, the team may be monitoring engines carrying 400,000 passengers.
We're sort of watching in the region of 8,000 to 10,000 engines, 24/7, 365 days a year.
Well, and that's the question, is this pretty normal or is it not?
We're looking at speeds, pressures, temperatures. We're just nipping problems in the bud before they happen. So people aren't waiting around in airports for the flight that's been cancelled or delayed again. So that's ultimately what we're trying to do.
The centre receives 1.5 million measurements every day, from anything up to 1,200 Trent engines at a time.
Typically a minute after the aircraft has sent that information, I can see it in graph form.
The data is analysed by computer, and if any unusual readings are detected, the engineers are automatically alerted.
Probably 95% of them we can very quickly sort of work out that there's nothing to worry about.
All the help desk engineers are experienced enough to solve any problem that might crop up.
I worked with Rolls-Royce engines hands-on, mainly in the Royal Navy for 13 years.
And they're just a phone call away from maintenance crews at key airports around the globe.
Yeah, I've just had an email if he's asking for data going back to January 2009, LP vibration data. Do you think you could answer that?
Back on the assembly line, this Trent engine has hit a problem, just 1 week away from its completion. The final module needed for the vertical stack has been held up on its way from Europe. Without it, the stack can't move along the line.
It's a turbine which actually drives the big fan at the front of the engine, which is mounted inside the fan case.
The engine is stuck in the assembly tower, but the fitters can't afford to lose any time. Instead, they've identified parts that can be fitted ahead of schedule.
It could arrive any time in the next hour, it could be in the next day, you know, we don't really know. So what we've done, we've jumped ahead and carried on building to try and get things done. As it is at the moment, we can't move it, we can't pick it up without that final module.
Any hold-up in the production process could cost money, so tracking down a replacement module is critical. And Kath Taylor is straight on the phone.
Can you guarantee that it will reach us before 6 a.m. in the morning? Yes? Yes.
At long last, it does arrive. And even though it's the middle of the night, the build will carry on. Working through the night is part of life for everyone on the production line. In Warwickshire, father and son Bob and Lee Blackwell are starting another night shift at the fan case factory.
It takes a bit of getting used to what it's like. It's quite hard. By Thursday, you're sort of ready for the weekend to catch up on your sleep. We tend to work the same shifts. On nights, we tend to get on each other's nerves. It's a testing shift, you know what I mean, when you're tired.
Tonight, they're working on a new fan case, bigger than any other, to be fitted to a new Airbus that is currently being built.
This is the biggest component that we've actually manufactured to date, 118-inch diameter, so it's a challenge. I mean, this is something that we're really proud of as an organisation. It's a first in everything that we're doing at the moment.
It won't be long before these parts are put together to make the first complete new fan case. When finished, it'll be the biggest Trent engine of all, with the lowest carbon emissions, and could become the third Trent engine in a row to launch a new jumbo jet.
It has actually been the fastest selling Trent engine in history. We already have orders for 1,000 Trent engines, and we will build that early next year. We will start testing it, and we hope to see it in the skies about 2 years from now.
But investment in new technology is worthless without investment in new people to keep manufacturing skills alive.
I'm currently an apprentice at Derby at Rolls-Royce as a manufacturing engineer in engineer maintenance.
Apprentice schemes like this are vital to British industry.
This is rotatives, this is my business that I'm working in. They mainly, again, deal with the discs, drums and shafts. In here we've got mainline shafts, so this is where they build the largest shafts which go through the main part of the engine. These are the coverings that go around them, so to make sure that the parts don't become damaged. You've got the various drilling machines down here. And then as you walk through here, this is where I work. This is the shaft supports office. Like, from a young age, I was always into like building things and like designing. And then the opportunity came round of like me getting the young apprenticeship, and also my family, like my dad's an engineer, my granddad's an engineer, my uncle's an engineer, so I've had a little bit of influence as well from them. But generally I just like engineering, and I like the fact of like designing and building.
I identified at an early age that, you know, he liked engineering because, you know, I think when he was about 8 I bought him a Connects, and, you know, in about the space of a couple of days he'd disregard, you know, he'd thrown away the manual and started making models of his own.
Like every apprentice, Neareyes can expect to spend 3 years or more learning the basic skills of his trade. So having a passion for it is really important.
Today I'm trying to make one of these control rods, which, as you can see, is here, and basically it allows the pilot to control the amount of airflow that's going through the engine and change various settings in the engine of the flaps and angles. You tell somebody you're 16, you work for Rolls-Royce, it's quite they see you as in a different light, and suddenly, like, that you're actually something special and something a bit different, because it's really quite prestigious to work in such a big company like this, at certainly the age that I am.
So first data midge, glued out from one end to the other.
Okay.
Second data midge, 90 degrees to it. Check that with an engineer's square.
Now I'm thinking, wow, what a change a couple of years can make to a life. Because going from schoolboy to engineer, it's quite a radical change, and I'm quite pleased with that change.
Once every engine is built and tested, its last stop is the customer delivery centre, where it has to pass scrutiny by engine inspector Mike Riley. It's a huge responsibility. His will be the last eyes to see inside the engine before it takes to the sky.
I've been at Rolls-Royce for 5 years now. In fact, this month. Before that, I was in the military as a helicopter technician on first-line maintenance. I've actually wanted to work for Rolls-Royce for some time before I came to work here, and it took me 2 years of applying before I could get in. So it's not the easiest place to get into.
Mike's is one of the most specialised jobs on the assembly line. Like a doctor doing keyhole surgery, he uses a borescope to inspect the inside of the engine.
Basically, every single rotating stage within the engine we'll look at, plus the combustion chamber. Literally, the whole of the inside of the engine is borescoped. This is the first stage HP compressor. At the moment I'm turning it rearwards. Usually the blades will come towards you. I'm just looking for any damage on the actual blade surface, leading or trailing edges. Occasionally you can get a little bit confused in there because there are so many blades. This is the first nozzle assembly that we're looking at, with all the hundreds of cooling holes on it. It's possibly the hottest part of the engine here. You know, practically a surgeon.
After Mike's final inspection, another Trent 700 engine is bagged up and ready to leave the factory. In a few days, it'll be in France and fitted to another Airbus 330 plane, just one of 300 engines built this year. These engines are Rolls-Royce's key to success, but it's keeping ahead of the competition that will secure the future for everyone in Derby. But right now, there's a big day ahead. Today, all eyes are on the performance of the Boeing Dreamliner, and of course, the Rolls-Royce engines that power it. It's a big day for the aeroplane out in Seattle, and an even bigger day for the team of engineers back in Derby, watching the preparations for the flight live online. As the aircraft prepares to take off and the engines fire up to full power, there's nothing anyone can do but wait, watch, and see what happens next.
And here she comes, the 787 Dreamliner.
Way to go, Rolls-Royce!
It's a massive coup to provide the engines for a new airliner's first flight. And it's something to be very proud of for the people who build them.
Quite an emotional moment for everybody involved, particularly for all the guys here who have built the engines, all the engineers who have designed it over the last 4, 5, 6 years. Some of these people have devoted their entire lifetime at work to this.
Ecstatic, really. Really delighted to see the aircraft take off after what's been a pretty long and tiring journey to get this far, really.
But the success of the flight can only really be gauged when orders for the new engine start coming in.
Great news, another order for 5 Trent 1000 powered Boeing 787 aircraft were placed this morning. Particularly good because it's quite a tough market at the moment, and so it does show testament to the technology in this engine that even in this market people are still placing orders. It's a great day to be in the job, it's a great day to be in Rolls-Royce, it's a great day for Derby.
For the 11,000 employees in Derby, it's another ordinary day, with more Trent engines to build. And in Warwickshire, it's the end of another shift for Bob and Lee Blackwell. But it's also the start of a new chapter in the story of the Trent engine, because the first fan case for the next engine in the Trent family is finally ready and about to be revealed.
We've organised the corporate comms team to come down to take a team photo. So we're going to get everyone that's been involved in the project together. There you go, look at that beauty. There you go. That's it. Work of art. It's a work of art.
It's something for Mark and his team to be really proud of. And a senior project manager from Derby is on his way to see the unveiling.
That looks really good. It's really good. Pull it this way a little bit further, and then have those two sitting behind it. We can all gather round the front, guys. If everyone comes in round the front, gather round. We've got to get some photogenic people. Got it.
This is a major thank you to all of you, and thank you very much for the fantastic effort you put in. This is so many firsts for us as a project. It's our first module and it's our biggest module, and a major milestone for our first engine. So thank you very much. Thank you.
That's great. Well done.